All right, topic 7.4, atmospheric carbon dioxide and particulates. So CO2 coming out of fossil fuel combustion is what we're concerned about. Although AP wants you to know it happens naturally, which is not really the problem. And then just driving down a road or the wind blowing, it kicks up dust, and that contributes to air pollution. Also not really what we're focused on, but there are some things we can do to prevent dust being kicked up, make it less detrimental. But nevertheless, there's natural particulates, there's natural CO2 all over. Let's get into that. So this is my favorite example, natural CO2, the 1980 Mount St. Helens eruption. So volcanoes, make a note of that, can release a lot of particulates. So volcanoes do erupt, continually around the world. They do release particulates, as you can see, and CO2. If you just check out this mountain back here, this is Mount Adams. Me and my son tried to climb to the top of that. Well, almost made it. We made it right about down there. And if you heard Mount Rainier, that's basically where this picture is taken from, the angle of Mount Rainier. Anyway, but natural. This is definitely natural sources that are out there. So things like respiration that we've mentioned before. Respiration, which is right here. Plants and animals, they both do respiration. They both release CO2, which is normal. It's part of the natural cycle of carbon dioxide, as is decomposition. Okay, which is when things die, they break down, and that releases that CO2. It goes up as they die, which again, normal. And then I have volcanic eruptions that I talked about. There we go. Volcanic eruptions. Now this is the key. Remember, I keep talking about this is where the carbon should be, but remember, we dig it up and release it from combustion. This is the problem. This is the issue. This is what drives global warming. Droughts, increasing dangerous storms, turbulence in the sky is increasing. Global warming. It's not from any of this part. This is all cool. It's this part. This is the problem point. So this is the observatory where they do a lot of space stuff. This is a really good place to look at outer space. Very clear skies, and we'll see why. This is in Hawaii, Mauna Loa on the Big Island, and this is called the Keeling Curve. Named after the scientists who started measuring carbon dioxide, CO2 at Mauna Loa in Hawaii, starting in the late 50s, I believe it was 58. And you can see it's just been a constant increase in CO2 and on up till today. It only goes to 210, so 2025, I believe, we're around 425 parts per million. So it just keeps going up and up. And we talked about this annual cycle. Remember, you get a peak kind of late spring as the plants come on in the northern hemisphere, because the northern hemisphere has so much more land. The plants have an outsized influence. Those plants are they're bigger population, because basically Asia and Europe, Eurasia is so huge. Anyway, top of Africa, North America, Central America, the top of South America, Indonesia. And then as the plants of the northern hemisphere go through spring, they start, absorbing all that CO2. CO2 decreases. It's going into plants. And then winter hits, plants stop photosynthesizing as much, and they stop absorbing that CO2 when it goes up. So under normal circumstances, we should have kind of a normal up and down within a certain level, right? But instead we got an up and down that goes up, 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 up. So this is normal to be up and down kind of, and this is abnormal because of what we're putting out into the atmosphere, which is these fossil fuels. This is why they do it in Hawaii. This is Hawaii. Look at how isolated this is. Look at all that space between the mainland. I believe that's around 4,000 miles. And look, there's not even any land visible on the other side. So this is a great place, very isolated. You'll get a very, very good reading from your equipment. There's no cities to interfere, put more CO2 into the air than need to be. So, variety of natural sources that we talked about over here, volcanoes. So these are all natural. Lightning can create nitric oxides. There's a lot of lightning happening we don't normally think about. Wildfires, which are driven right now largely from mismanagement of the forest, suppressing fire too much in the past, and now things are drier because of the Earth's getting hotter. So wildfires are increasing, so that's putting a lot of particulate. And that's particularly bad to breathe in, wildfire smoke. Here's area, or we call it non-point pollution sources. Just farms spread out all over the place, cities, just things going on in multiple places. Over here, this would be point sources. We got factories, power plants releasing emissions, and then you have mobile sources, things like cars, planes, trains, creating these emissions. But again, if we're looking at just natural sources, the only natural source is right here. But remember, this is the problem. Just look at it. Natural. We have to make the world. Have to take care of it so it takes care of us. All right. So this is a nice little diagram. Kind of shows you the size of these compounds. This top one would be PM 2.5. The smaller version. Okay, and this one below it, this blue sphere right here, this is PM10, so basically 10 microns. And then you'll see this is PM 2.5, all these little circles fitting inside of it. Human hair look like 5 of these, so 50 microns wide about. So that 5 of these PM10s can fit across your hair. So that's kind of relatively what you're looking for. And you've also all seen been around sand, I believe. Kind of gives you an idea of the size of sand right there. There shouldn't be anything. I guess, yeah, that wasn't anything. Again, another diagram. You might have an idea. Red blood cells need to fit through all areas of your body, so go all over your body. Very few places do not get touched by a red blood cell. So you can imagine PM 2.5, smaller than a red blood cell, can go everywhere. Everywhere in your body. The PM10, while still a problem, gets caught up in your upper respiratory tract. Doesn't get as far in your body. So let's go. These are the coarse, more coarse, and this just the upper respiratory tract. We consider this right here 2.5. Fine goes in the lower respiratory tract, like halfway through your lungs. And then it gets even smaller, very fine and ultra fine. Very fine gets in your alveoli, and then ultra fine through your whole body, systemic. Okay, so particulate matter, the smaller, the worse it is for your body. So again, natural sources. This would be respiration, just to remind. Plants included, and bacteria. I didn't mention that, we should. Bacteria, fungi. Okay, regular respiration, aerobic decomposition. Okay, there is anaerobic decomposition, which doesn't create CO2, but aerobic does. Bacteria, decomposers, and then these are natural sources up here. Examples. Sea salt getting kicked up from, you see dried out areas, like lakes that dry up. There's a lot of salt, like we have a lot of dry lake beds in Nevada, California, New Mexico. Those salt crusts can get in the air, cause issues. Pollen, we know that all the trees, weeds, grasses, that gets in the air. Ash from any kind of fires, volcanic dust, and dirt. Okay, and these are all natural things. So I mentioned before, just because you see a haze doesn't mean that's smog. It could be one of these natural things: dust, sea salt, ash, forest fires, or it could be just clouds, right? It could be vapor from clouds, especially here along the coast. So just you need to be able to describe research methods. Okay, so here, looking back at Mauna Loa, we got what is measured. Okay, we got to measure something. What is measured? CO2 concentration. Okay, how much CO2 is in the air? How? What they use is infrared gas analyzers. Similar to what we have in class. We have some analyzers we'll be using, if we haven't already, that do the same thing. Use infrared beam to go through the air and analyze, based on how that beam moves through the air, how much CO2 is in the air. And trying to add an infrared gas analyzers. Okay, and the design, I'll put that down here. And the design is you have the reading taken in an isolated area. Okay, because you don't want to be near towns where you have a lot of carbon dioxide being contaminating your readings. Okay, by doing it. If you're near a city, you're going to have a lot more CO2 from all the cars, the trucks, the factories, all the things. You need to be in an isolated area so you have the cleanest reading. There's no noise from any point sources. Okay, and oh yeah, so here is the prevailing winds just coming across thousands of miles of open ocean. Very little happening on the oceans. There are some ships out there, and then just really good air mixing before it gets to the sensors at the top of Mount Low. You do see they do need to pay attention to, there are eruptions, okay, but it's very well mixed. Okay, So even though these are some things we can't necessarily see all the time, especially CO2, particulates matter, particulate matter also, we can see it when it comes out as soot in an exhaust pipe. But we very well know, even these invisible aspects of our world around us can have a big impact on how we live here on Earth.